So this is the first lecture for fifth week. We're continuing our study of graph theory, but the problem this week is to colour the vertices of a graph and define a quantity called the chromatic number of a graph. It's an example of an invariant, something that only depends upon the isomorphism class of the graph. So isomorphic graphs will have the same chromatic number. So a vertex colouring means that you assign a colour to each vertex of a graph in such a way that no two adjacent vertices have the same colour. So we can define that formally by choosing, rather than actual colours, we'll initially use non-negative integers. So we'll use the natural numbers to denote the set of colours. So we just need a mapping from the set of vertices to the natural numbers. And the property I mentioned is expressed by this constraint that if we have an edge, that is, if we have two adjacent vertices u and v, that means they form an edge, then the colours associated to those vertices must be different. So if uv is an edge, C of u is not equal to C of v. C is really the map that assigns to a vertex its colour. And I'll call this the constraint. And I'll keep referring to this when we're colouring vertices. This condition I'll call the constraint. So that's what a vertex colouring is. Now, we can give some more definitions. One says that a graph is k-colourable, or can be coloured with k colours, if we can find such a vertex colouring which uses exactly k colours. So that means the image of our mapping C has size k. We don't need all the natural numbers, we only need k of them. Well, our graphs are finite, so we never need all the natural numbers, but we might need a bigger set. But if the graph is k-colourable, we only need k colours. If we can colour the graphs, always satisfying the constraint, we must always satisfy this constraint that no two adjacent vertices have the same colour. If we can do it in k colours, we can also do it in k plus 1 colours. So the question is, what is the least k for which G is k-colourable? And that least number is called the chromatic number of the graph. So that's the key definition in this lecture. The chromatic number is the least number of colours we need for the vertices so as to satisfy our constraint. Now, in practice, I may occasionally use colours if, say, we only need 3 or 4, but normally if I'm writing colours by hand, I'll use Greek letters to indicate the colours. So rather than 0, 1, 2 and so on, I'll be using Greek letters, but you can think of the numbers as corresponding to the initial letters of the Greek alphabet. Zeta, for example, is the 6th letter, but if I start from 0, that corresponds to 5. So if I'm doing things by hand, I'll use Greek letters, and so as to not confuse it with numbers, because we often use numbers to label the vertices themselves. An obvious thing to say is that if the number of vertices is n, if the graph only has n vertices, then obviously n colours suffice to satisfy our constraint. So certainly the chromatic number of any graph is less than or equal to the number of vertices. In fact, it's easy to find an example when it's equal to the number of vertices. If you take the complete graph on n vertices, that does have chromatic number n. Because if it had a lower chromatic number, that means that at least two vertices would have the same colour. But any two vertices are joined by an edge, so that's a contradiction. It would contradict our constraint. We wouldn't be able to satisfy this condition. So the chromatic number of the complete graph on n vertices is n. But we'll see examples in which typically the chromatic number is much less than the number of vertices. So let's now look at some easy examples. So let's start with the smallest chromatic number possible. We're assuming we've got at least one colour in our bag. So suppose a graph can be coloured with just one colour, supposing that the chromatic number is 1. Well, that means there can't be any edges, because as soon as you have an edge, you need two colours. As soon as you have a single edge on a graph, remember, if you have an edge, you must have two vertices. You can't have one end of an edge without a vertex. So we need colour alpha for one end, and we would have to take a different colour for the other end. So obviously, if the chromatic number is 1, we have just isolated vertices. So the picture would have to be like this. Now, that is a graph. If there's more than one vertex, it's not connected. But it is a graph, but it's a silly example of a graph, and I hope not to talk about such graphs. So assuming we have at least one edge, which perhaps I should have put as a hypothesis for this section, the chromatic number has to be at least 2. It turns out there are lots of graphs with chromatic number 2. They're the so-called bipartite graphs, which I'll define in a moment. But let's first of all start with the cycle graph. So remember, the cycle graph means that you put points around a circle or around a polygon. And you need at least 3 points. Once you only have 2 points, you'll have a graph that's not simple. And I should have said that in this colouring situation, I want to stick to simple graphs. I want to ignore the situation of multiple edges, and I want to ignore the situation in which we have a loop, because if we have a loop, colouring becomes impossible. So, as I wrote on the previous slide, all our graphs in this section will be assumed always to be simple. So that means that if I want to talk about cycle graphs, I need n to be at least 3. But if I have any even number of vertices, then the chromatic number is 2, because 2 colours will always suffice. Let me draw you an example, say with a hexagon, or 6 points around a circle. You have 6 points around a circle, or equivalently in graph terms a hexagon. We only need 2 colours, because if you start with colouring one vertex alpha, the next one has to be beta, but the third one can be alpha again, because it's not adjacent to the first alpha. And then you go beta, alpha, and because we've got an even number of vertices, it all works out, and we don't have a clash when we get to this position. So 2 colours suffice, and the chromatic number is therefore 2. It couldn't be any lower. However, if I have an odd number of vertices, then you can see that what happens, so for example, if we went down to the pentagon, for example, so let's suppose that this vertex here is not present, this last vertex, and supposing this is just a single edge here, then you see if I started alpha, beta, this colour here would have to be gamma, because it's adjacent to both beta and alpha. So if we have, that explains, if you have any odd number of vertices around a circle, you need 3 colours. So the chromatic number of an odd cycle is 3. Now, that actually is quite relevant for lots of graphs, because if any graph contains an odd cycle, for example, if it contains a triangle, a 3 cycle, then its chromatic number has to be at least 3, because even if you forget all the other vertices and edges of that graph, you need 3 colours just to satisfy the constraint for the triangle. What I'm really saying here, I haven't defined subgraph in these lectures, but it's defined in the notes. If you have a subgraph of a graph, then if you know the chromatic number of that subgraph, which often you do, if you have a complicated big graph, you might not know its chromatic number, but you will know the chromatic number of certain smaller subgraphs. You can say that the chromatic number of the big graph has to be at least as big as the chromatic number of any subgraph. Okay, so moving on, what about the graphs with chromatic number 2? So these are essentially the bipartite graphs. So a graph is called bipartite if you can split its vertex set into the disjoint union of 2 subsets. This symbol here means disjoint union. and all the edges go from a vertex in the first subset to a vertex in the second subset. You can't have edges within each subset. Such a graph is called bipartite, and essentially it's the same thing as saying that you need two colours, because I can colour all the vertices in the first set alpha. Well, I think I did this on a previous quiz. I called it black and white. So you can think of alpha as black, if you like, and beta as white, or vice versa. You can colour all the vertices of V1 one colour and all the vertices of V2 the other colour. And then you'll satisfy the constraint, because there are no vertices from alpha to alpha or from beta to beta. Sorry, there are no edges from alpha to alpha or beta to beta. So assuming we have at least one edge, the chromatic number will be 2. I've put less than or equal to here because you could in theory have a bipartite graph with no edges, but that's, as I said before, a silly case. So that's the idea of a bipartite graph, and there are many examples of bipartite graphs. They're easy. If you're given a graph, it's very easy to test whether it's bipartite. You try and colour it with just two colours, and so you can just keep going and see if you get stuck. So I've already given you one example, the even cycle, and the number of vertices is twice some other number. That's the even. That's the even cycle. The complete graph, the so-called complete bipartite graph, KPQ. That means you have two subsets, one of size P, one of size Q, and you join all the vertices. For example, let me do it for 2 and 3. You join all the vertices on the left to all the vertices on the right, if you like. K33 would be the utility graph, in which you're trying to join gas, electricity, and water to 3 houses. But the important thing is this can be coloured in 2 colours, because you can use alpha for the left-hand vertices and beta for the right-hand vertices, and you satisfy the constraint. And also another well-known example is the cube graph, the graph formed by the edges and vertices of a cube. This is actually a subgraph of the complete bipartite graph K44. I'm not going to draw that here because I'm going to talk about that in the next lecture. So those are bipartite graphs. One could go on in this way, actually. I mean, to say that a graph is K-colorable is really the same thing as saying it's what's called K-partite. You can split its vertex set into subsets and give each subset, it gives the vertices in each subset the same color. So we could also, one doesn't normally go beyond bipartite. At least I won't be going beyond bipartite. But one could just once, I'll use this name, tripartite. That would be when you can split the vertex set into 3 subsets. You can give all the vertices in the first subset the color alpha, all the vertices in the second subset the colour beta, and all the vertices in the third subset the colour gamma, or if you want, you can use red, green, and blue. And then the point is, the definition of tripartite means that you don't have, any edge has to go between red and green, or green and blue, or red and blue. There are no edges within each subset. Okay, so let me give you an example, actually, an example you've already seen of a tripartite graph to show you this is a useful notion. So this is the graph formed by the edges and vertices of an octahedron, a diamond-shaped solid. And we've seen this before in the previous lecture when I was using it as an example for defining walks and trails and paths and so on. But these are different representations of it. It's not obviously, doesn't look obviously the same graph, in that both these graphs, left and right, are isomorphic. They're isomorphic to the octahedral graph. But let me start with the one on the left, which I've coloured the vertices so that the adjacent vertices have the same colour. So you see here, I've got this is like the subset V1, if you like. Red, green is subset V2, and blue, these 2 vertices form the subset V3. And we've got all possible edges between those subsets. So in a sense, this could also be called the complete graph K222, in the sense we've got 3 subsets, each of size 2, and we've got all possible vertices between vertices in those subsets. But we're not allowed to have all possible edges, I should have said if I didn't, between vertices in those subsets. But we're not allowed to have edges within each subset. In fact, I've removed the edges here, which would violate that constraint. So that's an example of a tripartite graph. But if you reorganize the vertices and sort of move it so that the vertices with the same color are opposite each other, you get this picture on the right, which has the same connectivity properties. If you label the vertices with numbers and make them correspond, this will be an isomorphism that I defined last week. But the picture looks rather simple. We don't have this ugly crossing in the middle here, which doesn't represent a vertex. We still have some crossings, but it looks somewhat less confused, the picture. And in fact, if you stare at this picture, you can see the octahedron finally. If you think of this rectangle here as a sort of plane, it's not a regular octahedron, this is a rectangle, not a square, but if you think of that as like the plane, you can think of this as a sort of diamond that's tipped over a bit. And we have the top vertex here above the plane and the bottom vertex here below the plane. And you see we have an octahedron. Spot 4, you need to stare at it as an optical illusion. You need to stare at it a bit, but we have 4 triangular faces on top and 4 triangular faces down below. And that, as I said before, is a tripartite graph. And the key thing, therefore, is that the chromatic number of this graph is equal to 3. We need 3 colours. Exactly 3 colours will suffice to colour the vertices so that no 2 adjacent vertices have the same colour. That's the point. There's no edge joining blue to blue or red to red or green to green. Now, there's a very close link between the chromatic number of a graph, colorability, and the degrees of its vertices. So remember, the degree of a vertex is the number of edges. We have a vertex here. The degree is the number of edges that come in to that vertex. So if that vertex is called V, then the degree of V I'll write as D of V. And in this example, it's 4. Well, let's make it 5. Or you might prefer to write degree of V, so you're not confused. It's like the valency in chemistry. If this were bond, you'd use the word valency, which you can also use if you like. So what we do is, given a graph G, we look at the degrees of each vertex, and we use delta, capital delta, to represent to equal the largest of all those degrees, or the maximal vertex degree. So many of the graphs we've been looking at, all the regular graphs, all the vertex degrees are equal. In that case, it's easy. Delta is that number. So for the octahedral graph we've just done, all the vertex degrees were 4, so delta was 4, is 4. But in general, we'll have different vertices may have different degrees, and delta represents the largest degree in the graph. And I want to prove this lemma, which is a sort of first result on the chromatic number. It's quite elementary. It says that the chromatic number, we know it can't be bigger than the number of vertices, but we can do much better than that. It can't be bigger than delta plus 1. Okay, so typically in many of our examples, the vertex degrees will be much smaller. Every vertex degree will be smaller than the number of vertices in the graph. So this is a much stronger result. It tells us we can't beat the chromatic number will always be less than or equal to capital delta plus 1. Or another way of saying that is that the graph is delta plus 1 colorable. Delta plus 1 colors will always suffice to color the graph. Perhaps I should just give you an example before I start on that. So for example, the complete graph, let's just do the complete graph K4. K4 is a representation of the complete graph on 4 vertices. 6 edges. It's K4. K4 has, as we said before, chromatic number 4. I need 4 colours because all the vertices are connected. But the maximal edge degree is 3 because all the vertices have degree 3. So in that case, you actually need delta plus 1 colours. It's one of the few examples, as we'll see later, in which you need delta plus 1 colours. Often delta colours will suffice. Kn is the same. Kn has chromatic number n, but delta is n minus 1. Okay, so back to the proof. It's really quite easy, but I want to write this down formally. I should perhaps use induction. So I'm going to use induction on the number of vertices. Obviously, if I have 2 vertices, we're okay, because we've got 2 vertices, then we need 2 colours. Just have 2 vertices, we have to have an edge here. Well, we don't have to have an edge, but certainly the degree of each vertex is 1, so delta plus 1 is 2, and the chromatic number is at worst 2. So that's going to be okay. So we're okay for 2 vertices. Suppose the result is known to be true for n vertices, and we now have a graph with n plus 1 vertices. Then what we do is we label the vertices from 1 upwards, and we consider mainly the last vertex, in our list. We've listed the vertices, so Vn plus 1, and we sort of consider that separately and think of all the rest of the graph with all the other vertices on the left-hand side. So we have V1 up to Vn sort of on the left-hand side, and then we have our last vertex on the right. And this last vertex will be connected to a number of other vertices in the first list. So there will be edges going from the last vertex to some of the vertices in the rest of the graph, and these may also be connected, we don't know, or they may not be connected. So there's the rest of the graph. Blah, 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 blah. Now, the key point, however, here is that because the vertex degrees are at most delta, the number of edges here leading to the last vertex is less than or equal to delta, because the degree of the last vertex is at most delta. Now, if we've coloured the left-hand side of the graph here to satisfy the lemma, and that's our inductive hypothesis, then we know that delta plus 1 colours suffice on the left. We've just got to colour the last vertex so as to satisfy our constraint. But you see, we've only got delta edges here. Maybe here I've got 3 edges. And therefore, since we're trying to do the whole thing in delta plus 1 colours, I'll always have a spare colour. So whatever these colours are here, maybe alpha, beta, gamma, I'll always have a spare colour to colour the last vertex. In this case, I could colour it delta, say, a 4th colour. And I wouldn't be exceeding the delta plus 1 colours. And now you see we've coloured the whole graphs to satisfy our constraint, because the constraint just concerns looking at each edge, and all the edges on the left are okay, were okay before by hypothesis. We've just added the new edges crossing from left to right, and they now satisfy our constraint that no 2 have the same colour. So that proves the lemma. Okay, now I write that in text. There's a summary of what I've just said. So you start by looking at the graph with the first n vertices and edges between them. Delta plus 1 colours suffice for that. But in colouring the last vertex, given that this has degree at most delta, we'll always have a spare colour from the list of delta plus 1 available, and then everything works out. So this is really the key result, which is worth remembering. So the chromatic number of a graph never exceeds capital delta plus 1. And the question we're going to sort of ask ourselves for the rest of this week is, when is it true that when is it true that the chromatic number is actually less than or equal to delta rather than delta plus 1? That's the key question which I want to address. When is it true that the chromatic number, we can do better than the lemma? Okay, one final application in this video. We'll start addressing that question in the next video. I just wanted to give you a sort of amusing application of vertex colouring, and this is to timetabling of modules, particularly adapted at the moment when modules are online and we don't have to worry about having enough lecture rooms. Okay, so here are some modules. Forget the colours for the moment. Here are some module codes for third year modules in our department. And let me highlight 318, which is these are third year modules. This is Fourier analysis, I think. And I've written 351, which is representations of it. Let's change it to 251, and that would be level 6 discrete mathematics. Okay. The idea here is that each vertex, I say forget the colours for the moment, each vertex represents a module. And an edge means that one or more students are taking that module. Okay, so what I'm supposing here is that there is a student doing, at least one student, doing both Fourier analysis and discrete maths in the third year. And that's why I put an edge there. Okay, CSO5 is mathematical biology. That's a fairly popular course, I gather. So there are lots of students who do that and some other module. This has degree 5. Of course, this is a fake graph. I haven't actually done this research on modules, but anyway, that's the idea. You put an edge in between the two vertices if more than one student. Well, no, so if one or more students wants to do both modules, that means you've got to timetable them, in this case Fourier analysis and discrete maths, so they don't have the same slot. They have to have different lecture slots. And in fact, here we have the timetable. Might be too small to see, but I'm really talking about skills sessions, the live things. So we have the skills sessions for discrete maths here, Thursday 11:30, and that's followed apparently directly by something for Fourier analysis. You've got Wigman, Fourier analysis. So if there is, as I'm hypothesizing, a student doing both courses, that's why these slots can't be at the same time. And then you see the point is that the lecture slots correspond to the colours. And we want to colour the graph, we want to colour the vertices so that no edge has the same colour at both ends, because if it did, the students doing both modules would have their lectures at the same time. So the constraint that we're imposing to colour the vertices exactly guarantees that you're not going to have, that students can attend all the lectures they've registered for without clashes. Okay, and of course it's important to minimise the number of slots, particularly at the present time, because some of you are in Asia and you don't want skill sessions at 11 o'clock at night. So we want to minimise the number of lecture slots. That means minimise the number of colours. So that means take the least number of colours necessary to colour the vertices with our constraint. And that's the chromatic number of the graph.